Dear Professor and TAs, I'm Yiyun and we are Group 15 presenting on warehouse simulation using auto mode. Before we start, let me go through with you the flow of our presentation today. Firstly, I will give an overview of our project on warehouse simulation. After that, Haolun will go through data sanitization and analysis. And then Jinkang will talk about the input modeling, followed by Huang Wei, who will be presenting on the pass mover system. Last but not least, Yufei will discuss on the output analysis and give a conclusion. The demand for warehouse storage has been on a rise as e-commerce gained popularity in recent years. On top of the pandemic, the demand for warehouses in Singapore, in both e-commerce and logistics sector, has stockpiled in the second quarter of 2020 and will only continue to increase. It is therefore important to continuously improve on warehouse efficiency in catering to the rising demand. For our project, we aim to compare the performance of two differently designed warehouses in handling the same inbound and outbound rates of loads. Two types of storage facilities are being considered, namely the multi-shuttle system and the vertical lift module, whose configuration is as displayed on the right. And there are two layouts for comparison. The first one consists of 64 vertical lift modules as shown in the previous slides. The second layout makes use of multi-shuttle system to store small loads laid within its configurations and store other loads in the VLMs. We have developed 4 models in studying warehouse efficiency of different warehouse designs. Under layout 1, Model 1 and 2 are for the purpose in analyzing the impact of storage with consideration of load's popularity on warehouse efficiency. Model 3 and 4 will be analyzed together to represent layout 2 and compared with layout 1 to analyze the impact of separating small and big loads on warehouse efficiency. I will now pass the time to Haolun, who will explain on the data sanitization and analysis.
Thanks, Yiyun. Now I will share the part of the data sanitizations and analysis. Firstly, as we can see from the original data, it is a real inbound and outbound data with the key informations of the quantities, SKU ID, and the volume, as well as the date. Then our process is that we firstly want to match the outbound data with the inbound data. Then we want to find the inbound date and the outbound date for each item. Then we know about the waiting time and as well as the arrival rate. Then we will estimate about the approximate arrival rate distribution and the waiting time distributions. So firstly, I calculate about the daily balance based on these two data sets. However, it is found that some SKUs still have outbound records when the current balance is 0. As shown here, that the inbound date is day 7, while the outbound starts from the new date 1, while the daily balance is 0. Thus, this may be due to the lack of current balance in the beginnings. Then here is the logic I used. If the outbound quantity is smaller than the current balance, then the adjusted outbound quantity will be the real outbound quantity. However, if the outbound is larger than the current balance, then the adjusted quantity will be the outer balance left in the warehouse. The step 2 will be the update the quantities. Based on the volumes of SKU, we have categorized the SKU into large and small, and we update the quantity based on these two standard volume. For the small, it is 60 times 60 times 60, while the large is 150 times 100 times 100. So we update these two columns, and for the next steps, the quantity will all be the updated quantities. For the next step, our group rank up the popularity of different SKUs based on the total updated quantities in a year. The top 25% SKU with the largest updated quantity will be ranking 1, while the bottom 25% with the smallest update quantity will be ranking 4. Then we want to find about the inter-arrival time and waiting time. As we have already get about the waiting time and the inbound time for each SKUs. Then we calculate for each day what is the mean quantity. So as we can see that for both sizes, whether it's large or small, the higher rank we have, there will be a larger mean quantity and there's a higher turnoff with a lower mean waiting times. So here we estimate the arrival rate of the Poisson distribution, while the waiting time will be exponential distribution. Now I will pass time to Jinkang to talk about the distribution.
Thank you, Haolun. For input modeling, I will explain how our group utilized the sanitized data and came up with an inbound model that is appropriately representative. This slide summarized how we categorize our data from a raw data of 1 year with more than 3,500 SKUs that are of different dimensions and volume and enter the warehouse with different quantities and rate. We categorized it into 8 groups based on the size and storage time. By grouping it into 2 sizes, we can compartmentalize the VLMs and multi-shutter facilities into just 2 sizes, a simplified version from more than 3,500 sizes. However, this simplification greatly reduced the capacity of the warehouse. Next, grouping SKU into 4 ranks based on their storage time, which is also the waiting time in the warehouse before outbound process takes place. We prevent an overgeneralization of the probabilistic distribution of storage time, which increases the accuracy and realism of our model. Our group also did statistical goodness of fit tests for 8 different groups. As we can see from the graph, the storage time resembles an exponential distribution. We went on to carry out a hypothesis testing with chi-square and found that our inbound distribution will be rejected at a significance level of 5%. The closest of which is large load rank 4. However, as you can see, our model will definitely be rejected at a level of significance of 5%. But sadly, due to our limited knowledge on the transformation of distribution, we are not able to find a suitable distribution that is accepted at 5% level of significance. Hence, we decided to went on and use these distributions that we find that is the closest representations of the data in our model. Same set of arrival rate and storage time render variables will be used in our simulation for both layouts, which means that the decision of our simulations are based on these distributions and it is fair. Next, initialization bias exists when we initialize with an empty warehouse. By plotting the assembled averages, we determine the data that has to be deleted. Hence, only data collected after the 12th day is used for calculations.
Thank you, Jinkang. Now I'll be talking about path mover system, which is used to model the path that AGVs travel to pick up and drop off loads within the warehouse. From the warehouse layouts previously mentioned, we have the first layout of the VLMs. The path mover system is constructed with the actual dimensions of the warehouse layout, followed as closely as possible. Here, we can see that inbound goods arrive at the lower right area and the outbound goods depart at the upper right area. AGVs are modeled as vehicles traveling to 8 different zones of VLMs. Due to the complexity of the model, we have separately modeled the VLMs and multi-shuttle systems from the second warehouse layout. Here, we have the multi-shuttle systems modeled. Similar to the first layout, inbound goods arrive at the lower right area and outbound goods depart at the upper right area. AGVs travel to 8 rows of the multi-shuttle system. This slide shows the control points for the VLM model. Park Place is where the AGVs spawn. Load in is where inbound goods arrive. Load out is where outbound goods departs. And load drop 1 to load drop 8 are where AGVs pick up or drop off the goods for the respective zones of VLMs or multi-shuttle system rows. Similar to the VLM model, the multi-shuttle system model also has similar control points as shown here.
As for the AGVs, they are modeled as vehicles. For our model, we have set the vehicle capacity as 10 and 1 load per vehicle. They are traveling in a normal way and have the forward and reverse velocity as 1.5 meters per second. They have a curved velocity of 1 meter per second. The AGVs are set to return to park place every time it finishes a job before setting off for another job. For the name this, park place is the only place the AGVs start moving. For work list, as AGVs always return to park place after completing its job, only park place needs to set to all other points on his work list. For park list, all other control points set park place at its parking point. To prevent collisions of vehicles, locks are placed in junctions in the model. Control points capacity are also set to 1 for load drop 1 to load drop 8. Now, I'll be passing my time over to Yufei, who will be talking about the output analysis.
Thank you, Huangwei. I'm Yufei, and I will cover our output analysis part as well as suggestions for stakeholders. Here are 4 reports generated by AutoMode from our VLM model, ranked VLM model, VLM large model, and multi-shuttle model respectively. As our project purpose is to compare the efficiency of 2 layouts, we focused more on the average process time section in the reports. Average time of arriving process, timestamp process, searching for free space process, AGV collecting loads process, storing loads into VLM process, waiting process, transporting loads out from VLM process, as well as outbound process of loads were all computed in report files. In order to gain an insight on efficiencies of different models, we added up average time of all processes mentioned above as the total simulation time. From the last column of the report result table, the total time of VLM model is the longest, followed by multi-shuttle model, which are both far longer than the total time of ranked VLM model, followed by VLM large model. Here are some of our findings based on simulation reports. Firstly, loads stays longer in system with layout 1 than layout 2. Secondly, average time taken by the process of transporting loads into their shelves was largely shorter in layout 2 than layout 1. Thirdly, by sorting loads according to their popularity, total processing time of VLM system reduced significantly. Moreover, in order to study intangible relationships between in-system time and load popularity or size, we print out size, priority, and total in-system time for each load in simulation message files. By information extraction and data analysis, we plotted time distribution diagrams of small and large loads in both VLM and ranked VLM system with Seaborn library from Python. Blue stands for small size loads, while orange stands for large. From the 2 diagrams, it could be concluded that in-system time of small loads are longer and tend to have larger variance. After that, we plotted in-system time for loads of 4 popularity levels in all 4 models. Blue stands for loads with highest popularity, followed by orange, green, and red. From the average in-system time for loads with 4 ranks table, it's obvious that in-system time increased with rank level, which means that loads with higher popularity stay for a shorter time in system. From the findings above, we would like to give some suggestions to stakeholders of the warehouse system. Firstly, multi-shuttle system is more efficient than VLM system in warehouses by largely reducing inbound time. Thus, part of VLM system is suggested to be updated to multi-shuttle system in order to increase warehouse storage efficiency. Secondly, storing loads of higher popularity near to the entrance will largely decrease the total in-system transport time. Thirdly, total processing time of smaller loads tend to be longer and of larger variance. So, storing higher proportion of large loads may have an effect of reducing risk of average time delay. In conclusion, by simulating inbound and outbound processes in both Layout 1 and 2 by auto mode, our group concluded that warehouse design according to Layout 2 with multi-shuttle system is more efficient in storing SKUs presented in the dataset. And in order to further improve warehouse storage efficiency on top of the layout, warehouse designers may consider optimizing resource allocation, changing locations of entrance or exit, speeding up transporters, etc. That's all for our simulation project presentation. Thank you all for your listening.